Okay, so what we're going to be looking at in the next 2 or 3 lectures is a simple example to get you thinking in Haskell again. And the example we're going to be looking at is implementing a Sudoku solver. I'm going to do everything on my iPad from this point on in the module, but as I mentioned in the introductory lecture, you should also think about making your own notes on everything which I'm doing as well. All the code which I'm going to be presenting to you over these next couple of lectures is freely available on the webpage for the module. So I suggest that you download that and have a play around with that yourself. So before we get going, I just want to make sure that everyone understands what a Sudoku puzzle is and what the basic rules of the game are. So here is an example of a Sudoku puzzle, and you can see it's a 9 by 9 grid, and there's some numbers in the grid and there's some blanks. And the rules of the game is that you need to fill in all the missing squares to complete the Sudoku grid. And there's only one simple rule, or really 3 simple rules, and the 3 simple rules is that every row, every column, and every 3 by 3 box, so that's like these things with the dark red outside of them. Every row, every column, and every 3 by 3 box must have the numbers 1 to 9 exactly once. Okay, so that's the basic rules of the game. So let's see if we can solve this Sudoku puzzle by hand, at least for the first few squares, and see how we get on. So I'm going to focus on this particular row here, and that's a good one to focus on because it's only got 3 blank cells in it. So we know, to satisfy the basic rules of the game, that this row must have the numbers 1 to 9 exactly once, with no duplicates and no blanks. So if we look at the row here, we can see we've got all the numbers between 1 and 9, but we haven't got a 1, 2, and a 3. So we can think, where do these numbers actually go? Well, if you think about the 2 first of all, we can't place a 2, in this cell because we've already got a 2 here. So we can rule that one out. And we can't place a 2 in this cell because we've already got a 2 up here in this column. So that rules that one out. So by elimination, we need to place the 2 in here because it's got to go somewhere in this row and it can't go in either of the other 2 positions. So we're forced by the basic rules of the game to place the number 2 in there. So then we've got a number 1 and a number 3. Notice that we can't place the number 1 in this cell here because we've already got a 1 in this 3 by 3 box. So that would invalidate the rule of the game, one of the basic rules of the game. So we're forced then to place the number 1 in here. That's the only place it could go. And then by elimination, the 3 would have to go in here because that's the only place that it could go. There's only 1 cell left. So what we've seen here is by following the basic rules of the game, we've managed to fill in completely this first row. An interesting aspect of these kind of newspaper Sudoku puzzles is that they always have a unique solution. So there's always precisely one way to fill in all of the empty cells such that the basic rules of the game are satisfied. In fact, for this particular puzzle, which is called an easy puzzle, just applying the basic rules will completely solve the puzzle. There's always a forced next move where you have to put a particular value in a particular cell. But in general, you may need to think more deeply to solve more sophisticated Sudoku puzzles. So what we're going to be doing in the next 2 or 3 classes is we're going to be implementing a Haskell program to solve these kind of simple Sudoku puzzles. And the way we're going to come at this is we're going to start with a simple program, which we're then going to improve in a series of steps. So the simple program will be very inefficient, and then we'll improve it to end up with a highly efficient program which will solve any Sudoku puzzle at the end. This is similar to the way in which we wrote a countdown numbers game solver in the first year. You may remember we started with an impractical but simple solution, and we improved it in a series of steps, and we ended up with an extremely efficient program that could solve any countdown numbers game problem. So if you're interested in these kind of things, you might want to have a look back at the countdown numbers game solver from the first year. So just before we get going, I want to mention that the code which I'm going to show you, or the program which I'm going to write for you, is not my own. It's actually due to a good friend and colleague from Oxford, Richard Bird. And Richard was actually a professor in Oxford and a former head of computer science as well. So again, if you're interested in this kind of thing, you may want to also have a look at Richard's article. So let's now get down to writing some actual Haskell code. So what we're going to do first is we're going to make some basic type declarations. So I'm going to make some basic declarations. And I'm going to come at this in a top-down manner. So I'm going to write a Sudoku grid type, and then there'll be some components in that which we don't know what they are, and then we'll fill those in, and then so on until we've basically declared all the types that we need. So I'm defining a basic type here called grid, and a Sudoku grid is simply going to be a matrix of values. And a matrix is just a two-dimensional kind of array-like structure, which you're familiar with from your high school maths. So a matrix just is going to represent a Sudoku grid. And the grids are going to contain what's called values. So there's two things which I haven't told you what they are yet. So I haven't told you what a matrix is in Haskell, and I haven't told you what the value type is. So we're working in a top-down manner here. So now we need to think, well, how can we declare a matrix type, and how can we declare a value type? So for the matrix type, what I'm going to do is I'm going to make it a parameterized type. So we're going to have a matrix of type A, and A is going to be the element type or the component type or the cell type, and a matrix is simply going to be a list of rows. Okay, so a matrix of things of type A is simply a list of rows of values of type A. And then what is a row? Well, I'm going to define a row of things to be simply a list of things. So a row of integers, for example, would be just a simple list of integers. So if you think what's really going on here with the matrix type, a matrix is a list of rows and a row is a list of things. So a matrix is really just a list of lists. So this is a very natural way to represent a two-dimensional kind of data structure in Haskell. So the last thing I need to define now is what a value is. And you might think I'm going to say a value is an integer, which would be quite a reasonable thing to do. But I'm actually going to say that a value is a character. And that's a design choice I'm going to make it easier to display grids on the screen, to actually allow them to be printed. So a couple of points just then to re-emphasize before we move on. So the first point is that the matrix type and the row type are parameterized. So we haven't fixed a value type here. We've said a matrix of things of type A and a row of things of type A. And this is going to give us some flexibility, which we will use later on. Okay, so we've defined our data types to be a bit more flexible. The other point I want to make here is that essentially I could get rid of all of this stuff and just write that a Sudoku grid is a list of lists of characters. Okay, so I could have declared that, and that would be basically amounting to everything which we've seen above. A Sudoku grid is a list of characters. So you may say, well, why did I complicate it by defining 4 types rather than just having 1 type? And the answer is the matrix type, the row type, and the value type are useful for me. Okay, these are a bunch of intermediate types, and these will be useful for defining some helper functions later on. Okay, so we've defined our basic data type of Sudoku grids. Just to make sure everyone understands how the data type is working, I'm going to give you a couple of examples. So the first example I'm going to do is the easy grid, which we had at the start of the class today. So that's one which I found in a newspaper, and it's an easy puzzle. You can solve it by just applying the basic rules of the game. So how could I define the easy grid as a value in this data type? Well, let me write down the first row. Remember, a row is a list of things, and the things here are values, which are characters. So a row is basically just a string. It's a string of characters. So we had a 2, then we had 4 blanks. And this is why it's useful to use a char data type rather than an integer data type, because it's easy for me to count my spaces here and make sure I've got it right. And if I was just writing blanks here on the iPad, you couldn't actually see how many blanks I was having. So I'm going to represent a blank cell by a dot. So I've got a 2 and then 4 blanks and then a 1 and then a blank and then a 3 and then an 8. And that's my first line. And then I've got my second line, and what I have is 7 blanks, or 8 blanks. 1, 2, 3, 4, 5, 6, 7, 8 blanks. And then I have a 5. And then in the third line, I had a blank, and then a 7. And then I had 3 blanks. 1, 2, 3. Then the number 6. And then 3 more blanks. And so on. Okay, so if you look on the code, which is available on the web page, you'll find this kind of grid, and in fact all the stuff here defined in that code. So that's the easy grid. Let's define one more example. Let me define the empty grid, and in fact the Sudoku solver which we end up writing in the end will be able to solve the empty grid, okay, which is quite an achievement, I think. So I'm going to call this blank. So blank is going to be a Sudoku grid, and how am I going to define it? Well, the blank grid, well, what do I do? Well, I could use recursion here, or I could use some kind of list comprehension or something like that, but there's actually a library function which will make it very easy for me to write this empty grid. And the library function is called replicate. So what does replicate do? Well, you can kind of guess just by its type. It takes an integer, and then it takes a thing, and it's going to build you a list of that many copies of the thing. So for example, if you said replicate, oops, can't spell, if you said replicate 9, and then a single character dot, that will build you a list with 9 dots. So that's like an empty row. So that would build me the empty row, and then all I need to do is replicate that 9 times, and that will build me a grid with 9 empty rows. So again, I could have defined this using recursion, I could have used a list comprehension or something like that, but actually it's simpler just to use the library function called replicate, which makes it very easy for me to define the empty grid as a one-line Haskell program. So what we're going to do for the rest of today is work towards writing a function that decides if a Sudoku grid is what I'm going to call valid. And valid here is going to mean that the grid has no duplicate values in any of the rows or any of the columns or any of the boxes. Okay, so Sudoku grid is going to be a valid grid if it's not got any duplicates in any row, column or box. And the way I'm going to come at this is I'm going to use 3 simple helper functions. One which extracts the rows from a Sudoku grid, one which extracts the columns, and one which extracts the 3 by 3 boxes. So let me write these functions first of all. So I'm going to define a function called rows. And what rows is going to do is it's going to take a matrix of things, and it's going to pull the rows out into a little list. Okay, so it'll give me a list of all the rows in a matrix. In this case, it's very easy to define the rows function, because if we go back to our definition of what a matrix is already just a list of rows. So defining the rows function is very straightforward. I can just go here and I can say rows of a matrix is just the matrix. So you might think, well, this is a completely trivial little function. Why am I even bothering to define it? Well, you'll see that when we define the validity checking function, having this rows function, even though it's trivial, actually makes the definition of the function easier to understand. Okay, so we have this trivial little function definition here. So I want to actually simplify this definition, or I want to consider simplifying this definition. This is basically just defining the identity function. What the identity function does is takes a value and just copies it. And that's all rows is doing. So a cleaner way, if I wanted to define the identity function, I could get rid of this and I could just say rows is simply the identity function. And if you look in the standard library, the identity function is just id of x equals x. Okay, so this is a bit of a cleaner way to define what the rows function is doing. It does nothing, so we just use the identity function from the standard library. A simple property now of the rows function is this one. So here's a simple property. If I apply rows twice, I get back where I started. Okay, so if I take a Sudoku matrix M and I apply the rows function to it, that will give me a new matrix. In fact, it's exactly the same one. And then if I apply rows to that again, it's going to take me back exactly where I started. So if I apply the rows function twice, I get back where I started. So this is a trivial property here, but we'll see that these kind of properties, which we're also going to have for the columns and boxes function, will turn out to be important later on. Okay. Again, if we wanted to be clever, we could actually write this property in a more concise way. What we could say is if you compose using function composition, the rows function with itself, then you get the identity function. So what's going on here is we're using function composition, which is just normal function composition, which you've learned about in Haskell. And again, if you can't remember how this works in Haskell, maybe have a look back at the first year course. I think it's covered in lecture 7 on higher order functions. And all we're doing here is we're taking the rows function and composing it with itself and saying that that basically will do nothing. You'll get back the identity function. Okay, and again, this simple property, which seems completely trivial, will actually be useful to us later on. So we'll come back to this property later. So the next function we want to define then is one that extracts the columns from a matrix. So we've got a function called calls, and it's going to take a matrix of things, and it's going to extract the columns as a list of rows. Well, what does this actually mean? So let me explain with a simple picture. So let's define the columns function, or explain what the columns function does on a simple 3 by 3 matrix. And let me draw it as a picture here, but this is really a list of lists, as we know. So suppose we had the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and we want to think what resulting 3 by 3 matrix would we get. Well, this is very easy, because what we're going to do is we're going to take each column and pull it out as a row. So here's the first column. We have 1, 4, and 7, and we'll pull that out as the first row. So that will give us 1, 4, and 7. And then we have the second column, which is 2, 5, and 8, and we'll pull that out as the second row. That is 2, 5, and 8. Then we have the last one, 3, 6, 9, and we get 3, 6, 9. Okay, so what we've done here is we've taken each column one by one and made it into a row in the corresponding matrix. And you can ask yourself, what operation is this on matrices? Well, this is just matrix transposition. If you imagine the main diagonal of the matrix, let me change into red here, that's there. If you flip the matrix about the main diagonal, that's what the columns function has done. So it's just basically matrix transposition. It's flipping about the main diagonal. And this actually allows us to define the columns function in a very simple way. I can just write calls equals transpose, because there is a library function in Haskell which takes a matrix represented as a list of lists and just transposes it. Okay, so I don't need to actually go to the labor of manually defining the function. But again, if you want to do well on this module, think about how could you actually define the transposition function for yourself. That's quite a nice exercise using recursion or kind of list indexing or something like that. This function also has a useful property. And it's a similar or the same kind of property as we had with rows, but this one is less trivial this time. And what it says is if you apply the columns function twice, which means if you compose the columns function with itself, so you take the columns function, apply it once, and then afterwards apply the columns function again, that should get you back to where you started. And it's very easy to see, at least intuitively, by looking at the picture, that this is the case. Because if you flip or transpose a matrix twice, so if you flip it about the diagonal and then do the same again, you will get back to the same point that you started with. Okay, so this is just saying that if you transpose a matrix twice, you get back to where you started. Again, you might think, well, why should we care about a property like this? But we'll see later on that these properties of the rows, columns, and boxes function actually turn out to be very useful and important to us. So the last of these function is the boxes function. And what boxes is going to do is it's going to take a matrix of things of type A, and it's going to pull out the boxes as rows. Okay, so again, I'm going to illustrate what this does using a simple picture. So let me work with 4 by 4 matrices here, so I don't need to draw quite so much stuff. And let's imagine that we have 2 by 2 boxes in them. So let me kind of make the border of the matrix a little bit thicker here. So there's a 4 by 4 matrix. And let me draw another one over here. If I was clever, I could copy it, but I'm not, so I won't. So there's the resulting matrix here. And again, you can draw the border a little bit thicker. There we go. Okay. So what is boxes going to do on these 4 by 4 matrices with these 2 by 2 boxes? So let me fill in some numbers here. So let's fill in numbers 1 to 16. So we're going to do the same kind of thing as we did with columns, but this time we're doing it with boxes. So here's the first 2 by 2 box. What we're going to do is pull this out as the first row. So over here we will get 1, 2, 5, and 6. And then we have the second 2 by 2 box, 3, 4, 7, and 8. And we have that over here. So we get 3, 4, 7, and 8. And then similarly, we get the 9, 10, 13, and 14. That will become this row. We get 9, 10, 13, and 14. And then we get the last one. We get, oops, in the wrong order, but you see what I'm doing. We get 11, 12, 15, and 16. Okay, so we've simply taken each of the 2 by 2 boxes, one after the other, and pulled them out as a row. Defining this function is actually, it's a little bit tricky, so I'm not going to go through the details. The details are actually not that important, but if you want to see how to do it, have a look at the online code. And I think it's still quite a messy definition. If any of you work out how to do this in a cleaner way, be quite interested in seeing how you did it. So there's a property here again. And the property is exactly the one you'd expect now. If you apply the boxes function twice, you get back where you started. Okay, so let's have a look to see why this might be the case, and maybe change to a different color here for a second. If we take the first 2 by 2 box, that became this row over here. Okay, and then if we did the same thing on this side, so if we take now the first 2 by 2 box of this one and we push it back over here, that's what we get. We extract it as the first row. So what you're seeing here, if you kind of generalize this and look at all the boxes, is if you apply the boxes function twice, you'll get back where you started. So here we had this 1, 2, 3, 4, and that moves over to the right hand side, and then correspondingly it will move back over when we apply the boxes function again. Okay? So if we apply the boxes function twice, we'll get back to where you started. Again, may seem like a useless property, trivial property, but it's going to prove to be very useful to us later on. So this brings us to the point now where we can actually define what it means for a Sudoku grid to be valid. So remember, a Sudoku grid is valid if it has no duplicates in any row, any column, or any of the 3 by 3 boxes. So let me define my little validity checker now. So valid is going to take a Sudoku grid and give me back true if it's valid and false if it's not. So how am I going to define this? So because I've got these three little helper functions, it's actually going to be very easy to define it. All I'm going to say is if all no dupes rows G, all no duplicates in the rows, all no duplicates in the columns, and all no duplicates in the boxes. Oops, boxes G. And this is essentially just a one-line definition which I've written over 3 lines here because otherwise it wouldn't fit on the screen. So a grid is valid if there's no duplicates in any row, any column, or any box. And this basically just translates this directly into Haskell code. But of course there's a few bits and pieces here that we don't know what they mean, so we need to just kind of make sure we understand these. First of all, what's this guy? Well, this is just logical AND. Okay, saying there's no duplicates in the rows, and there's no duplicates in the columns, and there's no duplicates in the boxes. Then we need to think, well, what does the all function mean, and what does the no duplicates function mean? So let's do that. So all is actually a simple library function, and what all does is you give it a function which returns true or false, which is called a property or a predicate. And you give it a list of things, and it's going to give back true if the property is true for everything in the list. So for example, if you started up GHC and you said, oops, that's wrong. If you started up GHCI and you said all even, and then the list 2, 4, 6, it will give you back the result true, because everything in that list is even. So how is all actually defined? Well, there's a nice little one-line definition for this in the standard library. So if you have some property P and some list X's, all we're going to do is AND P of X such that X comes from X's. So what's going on here is we're taking each value in the list one at a time. We're applying the property P to it in a list comprehension. This will give us a list of trues and falses, and then we're ANDing them together. So you only get true back here if everything in this list is true. So the property P is satisfied of all the elements. Lastly, we need to define the no duplicates function. So this is not a library function this time, so I'll define it. And it's got an interesting little type. So the type is this one. So what no duplicates does is it takes a list of things of any old type A and it returns true or false depending on whether there's any duplicates in the list or not. But of course, when you're checking if there's duplicates, you need to compare things for equality. So you need a little equality constraint on here because, for example, you can't check if a list of functions contains duplicates because you can't compare functions for equality. You can only compare certain types for equality. So how do we define no dupes? Well, no dupes, we'll do it with recursion. We say if there's no duplicates in the empty list, that is true, and no duplicates in a non-empty list. Well, there's various different ways we could do this. What I'm going to say is if it's not the case that the element occurs again, so LM detects whether a particular value occurs in a list, and we want the list never to occur again, otherwise it's a duplicate, and we want there to be no duplicates in the tail of the list, the remainder of the list. Okay, so that's all we're going to do today. We've basically just reviewed what Sudoku puzzles are, set up some basic data type declarations, and we've defined this function called valid up here, which decides if a Sudoku grid is valid. So there's no duplicates in any of the rows, any of the columns, or any of the boxes. So let's start by refreshing ourselves about what the rules of the game are. So here is a Sudoku grid. It's got rows, columns, and boxes, and some numbers are filled in and some numbers are not. And the name of the game is you've got to fill in all the blanks such that each row, each column, and each of the 3x3 boxes in red has each of the numbers 1 to 9 exactly once. So no duplicates and no blanks. So what we did last day is we defined a bunch of new type declarations, and we defined some simple functions which we're going to be using today. So I want to start by reviewing these as well. So here's the basic definitions for types which we had. So we said a Sudoku grid is going to be a matrix of values, and then a matrix of things is going to be a list of row of things. A row of things is simply going to be a list of things, and then a value is going to be a character. And as we mentioned last day, essentially a Sudoku grid is basically a list of characters, but having some of these intermediate data types, in particular the parameterized type for matrices and the parameterized type for rows, is going to be useful to us today. So that's our basic data type declarations. Then last day we also defined some simple functions as well. So we defined 3 functions called rows, columns and boxes, and each of these simply takes a matrix of things and pulls out the corresponding entries as rows. So for example, the columns function takes a matrix of things and pulls out each column as a row. And as we saw last day, that was just defined by simple matrix transposition. Now what we ended up with last day is we defined a simple function called valid, which checks to see if a Sudoku grid is valid. And validity here simply means that there's no duplicates in any row, any column, or any box. So for example, the number 2 doesn't occur twice in a single row, or a single column, or a single box. And also what we looked at last day, which maybe seemed a bit kind of strange and trivial last day, but we'll see why they're actually useful today, is 3 properties of these simple functions, rows, columns, and boxes. And the properties are that if you apply the rows function twice, you get back where you started. Similarly, if you apply the columns function twice, you get back where you started. And if you apply the boxes function twice, you also get back where you started. And again, these may seem like trivial little properties, but we'll see that they're actually very useful today when we come to implement our first Sudoku solver. So let's actually implement our first Sudoku solver now, and I'm going to call this a basic solver. So we're going to implement a basic Sudoku solver. And the way this is going to work is we're going to give our solver a Sudoku grid as input. So that may be a partially filled in grid like the easy grid which we saw last day and on the cover page today. And then what we're going to give back is we're going to give back a list of all possible grids that solve the problem. And actually you can see here we're solving a more general problem than the one we actually want to solve. Each Sudoku grid that appears in the newspaper only has a unique solution. So in principle, we could make the solve function take a single grid and give back the single grid that solves it. But actually we're going to solve a harder problem here. If a grid has more than one solution, we're going to give back all of them. And this is a kind of common thing in algorithm design. Sometimes it's easier to solve a harder problem, like returning all possible solutions to a Sudoku problem, rather than giving back a single possible solution. And of course, if we wanted a single solution, we'll just take the head of that list, and under lazy evaluation, that will do the minimum amount of computation necessary to just give us one unique solution back for the puzzle. Okay, so how is our basic Sudoku solver defined? So I'm going to give you the definition, and then we will figure out how to define the parts which we haven't seen yet. So it's going to be the composition of 3 functions. So we're going to filter valid solutions in the end. After, we'd use a function called collapse. After, we apply a function called choices. Okay, so we've got a simple function composition here. We're composing 3 functions. In order to solve a Sudoku grid, we're going to first of all apply a function called choices, which we haven't yet defined. Then we'll pass the output of that into a function called collapse, which we haven't yet defined. And then in the end, we will filter out all the Sudoku grids which are actually valid, i.e. no duplicates in any row, any column, or any box. So this is a simple one-line function definition using function composition. If you're not so familiar with function composition yet, I can write it as a more regular Haskell program. I could say if you want to solve a Sudoku grid, you filter valid, and then you apply collapse beforehand, and then you apply choices beforehand. Okay, so what you can see here is we're taking the Sudoku grid G in, we're applying the choices function, then applying the collapses function, and then filtering the valid things out. And this is exactly the same as the one-line definition, which we have here, but I prefer the one-line definition because we haven't needed to name the argument g, and we've got rid of all the brackets. And it really expresses the intuition that solve is just a composition, or a pipeline, if you like, of 3 different functions altogether. Okay, so let me just get rid of this one. So what we need to do now is think, how can we define the 2 parts of this definition that we haven't seen yet? How do we define choices and how do we define collapse? So this is what we're going to do now. So first of all, we're going to apply the idea of making choices. And the idea here is a very simple one. What the choices function is going to do is it's going to take each blank cell in a Sudoku grid and replace it by all possible choices between 1 and 9. So let me explain what this means with a simple picture. So let's draw the top left-hand corner of the easy Sudoku grid, which you've been working with. So there's the kind of corner 9 squares here. And we had a 2 in here, and we had a 7 in here, and these values were given to us. And then what the choices function is going to do is take an initial choice matrix, or an initial Sudoku grid like this one, and it's going to replace each of the blank cells by all possible values 1 to 9. So in this cell we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. And similarly in this cell we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. I should have chosen a slightly smaller pen size here. So on here, similarly for each of these boxes, just fill them all in. Each of the blank cells is going to get the number 1 to 9. And notice that we don't make any effort at this point to try and be clever. Because, for example, we have the value 2 sitting here, so there's no point in having any 2's in anywhere else in the row, or anywhere else in the column, or in fact anywhere else in that top 3 by 3 box. But we're not trying to be clever here. We'll do that later on. The choices function just simply replaces each blank cell by all the possible numbers between 1 and 9. No attempt to be clever at all at this point. So let's define the choices function now. So what choices is going to do is, well, first of all, we're going to define a little type for what choices are. So choices with a capital C is going to be a list of values, like 1 to 9. And then the choices function is going to take an initial Sudoku grid, such as the easy grid, which we've been working with. And then what it's going to give us back is a matrix of possible choices for each cell. And now you see why the matrix type is parameterized, because, oops, that's the wrong thing. Because here we're having a matrix of choices. We're no longer just having a matrix of values, which are single characters. Now we're having a matrix whose entries are lists of values, or all possible choices. So we see now the advantage of having this parameterized data type for matrices. So we can define the choices function now. This is a very easy one to define. If you give me a Sudoku grid, what I'm going to do is a double map. So let me write this down and then explain how it works. So what I'm going to do is I'm going to map the map of a choice function across the Sudoku grid. And the choice function I'm going to define in a little where clause here. It's going to be a small local function which simply replaces each blank cell in a Sudoku grid by all the numbers 1 to 9. So this is a very easy function to define. If you give me a value, v, which is a character, I test, is the value a blank, which is a dot? If it is, I'm going to replace it, or return, rather, the list 1 up to 9. Otherwise, I'm going to just put the little value in a list. And I have to do this because I'm returning a matrix of choices. And all the map here is doing is I've got a double map here. The double map is simply applying the choices function to every cell in a grid. And if you don't understand how the double map works, think about the types, maybe draw a little picture, and everything should become clear, hopefully. So that's the choices function now. The next function we need to define is collapse, which is sitting in the middle here. So what does collapse do? So let's have a think, first of all, about the type of collapse. So what collapse is going to do, if you work out its type, which you can work out just by looking at the components which surround it, it's going to take a matrix whose elements are lists of choices, and what it's going to give you back is a list of matrices. Okay, so it's going to take a matrix of lists and give you back a list of matrices. And you can then think, well, what does this function actually do? Well, what it's going to do is it's going to collapse a matrix of choices to a choice of matrices by producing all possible combinations of choices for each cell. And that's a bit of a mouthful, but the idea is actually very simple. So let me explain this again with a picture. So let's have the top left-hand corner of our easy Sudoku grid. And what we have is we have the value 2 sitting there in the top left-hand corner. And then when we applied the choices function, it will have a 1, 2, 3, 4, 5, 6, 7, 8, 9 sitting in that blank cell there. And it will replace that blank cell sitting next to it. Similarly, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what the choices function would do. And now what collapse is going to do is for each of these cells where there is a choice to be made, so there's 2 cells with choices to be made, it's going to consider all possible combinations of choices. So for example, out of this function, we could have this choice. So the 2 is already fixed. We could pick a 1 for the second cell and a 1 for the third cell. Or we could do something different. We could pick a 2 here, that's already fixed. We could keep the 1 here, we could pick a 2 here. Or similarly, we could have 2, 1, 3, and so on. And we could have kind of 9 possible choices for the third cell there. And then we could go down and say, well, what about the second square? Well, the first cell is still fixed. The second one could then click over to 2, and then you could have a 1 here, and then so on and so on. So you can see here that in this case, if we just applied collapse to this little part of the choice matrix, then you would actually end up with 9 squared things coming out, so 81. So really, I don't think collapse is actually the right name for this function. Maybe I should have called it explode, because it's actually going to explode a matrix of choices into a choice of matrices. So that's basically what the collapse function is going to do. It's going to take a matrix where the entries are lists, and then it's going to consider all possible combinations of choices that you could make for each of those cells. So in order to define this function called collapse, what we're going to do is first of all define a function that produces all possible combinations of elements from a list of lists. So let's think about how to define this first of all. So I'm going to define a function called CP. I'll explain in a moment why I've called it CP. And what CP is going to do is it's going to take a list of lists and it's going to choose all possible ways of choosing one value from each list. So I've got 3 lists here. I've got a 1 and a 2, and then a 3 and a 4, and then a 5 and a 6. So I could choose the 1 from the first list, the 3 from the second list, and the 5 from the third list. That'd be one possible way of choosing a value from each list. Or I could choose a 1 from the first list, a 3 from the second list, and a 6 from the last list. Or I could choose, for example, a 1 from the first list, a 4 from the second list, and a 5 from the third list, and so on and so on. So what this function is doing is it's taking a list of lists, in this case 1, 2, 3, 4, 5, 6, and it's choosing all possible ways of choosing one value from each list. So I could choose a 1, a 3, and a 5, a 1, a 3, and a 6, and so on and so on. And I've called this function CP because it's essentially computing the Cartesian product of a list of lists. You may remember from your mathematics courses in the first year, if you write A times B, where A and B are sets, That's going to be the set of all pairs AB such that A is an element of A and B is an element of B. And that's called a Cartesian product of sets because it's taking two sets, A and B, and giving you all possible ways of choosing one element from the first set and one element from the second set. And the CP function does essentially the same thing, but it's working with lists rather than sets. So then we can think, well, how do we actually define this CP function? And it's very straightforward to define. So I'll define CP. It takes a list of lists of A things, and it's going to give you back the same, a list of A things. And it's got a simple base case. If you give me a list with nothing in it, I'm going to give you back a list with the empty list in it. And I'll come back to this in a minute because it's an important point for the base case. And if you apply CP to a non-empty list of lists, so you've got a pattern here. You have X's is the first list, like the 1, 2. X's is everything else, like all of that. Then you think, well, what am I actually going to do? Well, we can define this using a simple list comprehension. We're going to compute the list of all lists, Y followed by Y's, such that Y is an element of the first list. So this is going to choose, this generator here, is going to choose all possible values Y coming from the first list. And then what we're going to do is recursively choose all possible lists Y's from CP of X's. And that's all possible ways of recursively processing the tail. And then we will package these two values up together as a list. Okay, and again, you might need to think a bit and maybe try and reconstruct this definition for yourself to see why this achieves the desired behavior. Now we can come back to the base case. You might think, well, why in the base case did I return a list with the empty list in it? Why didn't I just write the empty list here? And the answer is, and you can check this out for yourself, if I just return the empty list here, this would make this function always return the empty list. Okay, and you can try and figure out why that is the case, but you can try it out practically as well, just to see that you actually do need to return a list with the empty list in it as the base case. Okay, so now we can use the CP function, our Cartesian product function, to actually define what it means to collapse a choice matrix. So I'm defining the function called collapse now, and it takes a matrix of choices, so a list of possible things that each cell could be, and what we're going to get back is a list of all possible matrices that we get by choosing one thing for each cell. And it's a very simple one-line definition now. So if I give you a choice matrix M, what I'm going to do is apply the CP function in a certain way. What I'm going to do is internally, I'm going to map CP across each row of the matrix. And that's going to collapse each row. Okay, so this part here is going to collapse each row. And then what I'm going to do at the outer level is apply CP once more, and this will collapse each column. So this is going to collapse each column. And again, you may need to stare at this bit, maybe experiment with it, and maybe even try and rewrite it yourself to convince yourself that this actually does the right thing. So now, actually, in a very short amount of code, we actually now have our working Sudoku solver, our first working Sudoku solver. So if we go back to here, quite a few slides back, here is our Sudoku solver. What it's going to do is you give it a Sudoku grid. It's going to apply the choices function first of all, and that will replace each cell by all possible choices 1 to 9. Then you're going to apply the collapse function, and that will consider each possible value that you could have in each cell by considering all possible combinations of those values. And then finally, we're going to filter out the resulting grids which are valid. So they satisfy the basic rules of the game, that there's no duplicates in any row or any column or any box. So this is essentially a one-line program that solves Sudoku puzzles. But there's a little problem, and the problem is a practical one. So if you go to the web page for the module and you download the Sudoku code and you load it into GHCI and you start it up and you say solve the easy grid, it's just going to sit there. It will never terminate, basically, not in your lifetime anyway. And in principle, this Sudoku solver works, but in practice it doesn't. And in practice it doesn't because the search space in this case is too big. If we go back to our grid, right back at the start here, if you count the number of blank squares here, there's actually 51 blank cells in this grid. So if you think what the collapse function is going to do, out of this function here is going to come 9 to the power of 51 grids. Because for each of those empty cells, there's going to be 9 possible things that it could be, and collapse will consider all of those, so you're actually going to get 9 to the power 51 grids coming out here, and that's a number which has approximately 49 digits in it. Okay, so you can try that out for yourself. What is 9 to the 51? It's a 49-digit number, roughly. That's not going to terminate in anybody's lifetime. So in principle, this Sudoku solver works, but in practice, it doesn't. So we need to think a little bit more carefully. What we're going to do then is think about trying to prune the search space down. So we're going to think about pruning the search space. And the way we're going to do this is very simple and very obvious. So when we considered the top left-hand corner of our easy Sudoku grid, which I'll draw again here, we had a 2 here and a 7 here. And when we applied the choices function, it just blindly replaced every single blank cell by all possible numbers between 1 and 9. But that's nonsensical because, for example, in the first row we have this number 2 and down here we have a number 7. So what this tells us is nowhere else in this row should we ever have a 2 because that would invalidate the rule of the game. Nowhere else in this column should we have another 2 because that would invalidate the rule of the game. And in fact, nowhere else in this 3x3 box at the top left-hand corner should we have a 2. So there was no point in considering a 2 anywhere there. And it's the same with a 7. There's no point in considering a 7 anywhere in the row or the column with the 7 in it or the 3x3 box with the 7 in it. So the idea here is that we can prune out any choice that occurs as a single entry in the corresponding row, column, or box. Okay? So what we're going to do then is we're going to write a simple function called prune, and let's think about the type of it first. So what prune is going to do is it's going to take a matrix of choices and it's going to give us back a matrix of choices, and it's going to prune out any choice that occurs as a single entry in the corresponding row, column, or box. So how am I going to define this? So this is going to be another one of our one-liners. So we're going to assume, or we're going to define actually, a helper function called prune by. And what prune by is going to do is allow us to prune by the boxes, the columns, and the rows separately. So what we're going to do is we're going to have a simple function composition. We're going to prune by the boxes after pruning by the columns, after pruning by the rows. So this is going to prune out, we consider this part, for example, this is going to prune out any value which occurs as a single entry in the corresponding row. Then we'll prune out any value which occurs as a single entry in the corresponding column, and then we'll prune out any value that occurs as a single entry in the corresponding box. So we're going to prune the rows, columns, and the boxes. And the prune by function is a clever little helper function. And what prune by is going to do is you give it one of these functions, rows, columns, or boxes, and what it's going to do is a simple function composition. And this is the clever part. So what prune by is going to do is you give it a function f, which will be one of rows, columns, or boxes, and then it's going to be a simple function composition. And what the function composition is going to do is imagine f was the columns function. Okay, so we'd apply the columns function. That would extract the columns as rows. And then what we would do for each of those rows, we'd apply a function called reduce, which we haven't yet written, and then we'll put the columns back together. And here we're exploiting the fact that when you apply, for example, the columns function twice, it gets you back where you started. So this is letting us prune the columns by transforming the columns into rows, operating on those rows, and then putting the columns back together. And it's the same for the boxes and the rows as well. Okay, so this is a clever little function which is exploiting the fact that we can turn boxes into rows, for example, operate on those rows, and then turn them back into boxes. So we don't need to write a separate pruning function for columns and rows and boxes. We just write one function and we're done. So now we can think, well, what does this little magic helper function called reduce actually do? Well, reduce is very simple. Let's think about its type. What reduce is going to do is you give it a row of choices, and it's going to give you back a row of choices where any single entries have been pruned out of the corresponding other choices. Okay, so again, that's a little bit of a mouthful. What does this actually mean in practice? Well, what it means is if you give me a row of choices, so suppose the first cell had the choices 1, 2, 3, 4, and the second cell had no choice, it was just a 1, and the third was a 3 and a 4, that's the two possible choices there, and the fourth was no choice, you have a 3. What reduce will do is it will look for any entries in this row of choices which are single. So here we've got a single 1 and a single 3. And because we've already made the choice that this must be a 1 and this must be a 3, there's no point in considering the 1 here or which other one, or the 3 here, okay, and the 3 here as well. Okay, so we could eliminate those 1s and 3s from the other entries. So what we should get back then is if we eliminate or reduce, we should get 2, 4. So the 1 and the 3 have disappeared because these occurred as single entries elsewhere. We get the 1 here, then we get a 4 here because the 3 disappears because it's a single entry elsewhere, and we get a 3. Okay, so what the reduce function is doing is eliminating choices which have no possibility to ever succeed. So again, for example, there's no point in considering this choice 1 here because we already have a 1 here, and there's no point in considering this 3 or that 3 because we already have a 3 here. So we eliminate these and we get down to the 2, 4 here and the 4 here. So I'll leave it as an exercise for you to try and define the reduce function. Again, I mentioned right back at the start of the course, if you want to do very well with the Advanced Functional Programming course, I'm going to be setting you some exercises from time to time. And this is one of the exercises. Try and define the reduce function for yourself without looking at the notes. And it's quite an interesting exercise to do that. There's lots of different ways you could do it. Okay, so we've got the idea of pruning now. Now we can define a new Sudoku solver. So let me define our second Sudoku solver. I'll call it solve2, and it's going to be defined very similarly to before. It's going to be filter valid after collapse, after prune, after choices. So it's a big function composition again, except what we've done now is we've introduced our pruning helper function here between the choices function and the collapse function. And this will eliminate any choices which are silly or not going to ever lead to a solution because they occur as a single entry in the corresponding row, column, or box. For example, if we see a 2 in a particular row, we can eliminate that in the rest of the row, the rest of the corresponding column, and the rest of the corresponding box. So we can ask ourselves, does this make our Sudoku solver any better? And the answer is it does make it a bit better. For the easy grid, it leaves on average about 2.4 choices per square or per cell. But this still leaves a very large number of grids coming out from the collapse function. Previously, for the easy grid, we had 9 to the power of 51, which I think was a 48-digit number or something like that. The number coming out of here is approximately 10 to the 24 grids. coming out of here now. So it's reduced it. It used to be 9 to the power 51. We've reduced it to 10 to the power 24, but it's still an astronomical number and actually not feasible for solving Sudoku puzzles. So again, you can try this out for yourself. Try starting up GHC. So start up GHCI, say solve to the easy grid, and it's just going to sit there forever because it's trying to explore the search space up here of around 10 to the 24 possible grids coming out of the collapse function. So we need to think a bit more deeply. The solution is quite a simple one. It's the idea that we can repeatedly prune, because once we eliminate entries which occur as single entries somewhere in the grid, those choices are not particularly, they're never going to lead to a solution. It may be the case that there's now new single entries which we can then prune again. Okay, so this is going to lead us to a new function or a new idea of repeatedly pruning. So if I take the reduce function and I apply it to the output which we got from applying it previously. So once we reduced once with this particular example, we eliminated some values and we got down to a 2 and a 4 and a 1 and a 4 and a 3. But in doing so, now we have the fact that this one here must be a 4. Previously, I think we had a choice of a 3 and a 4 there. Now we've only got a choice of a 4. So if we reduced again, maybe we can do better. And in fact, we can do better because we see that we have a 4 here. So if we reduce, that's going to give us a slightly smaller choice list. So we'll get 2, 1, 4, and 3. Okay, so this is taking the output from the previous example, which was this one here, and then if we reduce again, we manage to eliminate another choice here. So this leads us to the idea of iterating the pruning process. We can kind of keep iterating this idea of eliminating single choices from anywhere else in the grid until nothing changes, and what that means is we've reached a so-called fixed point. Okay, so let's see how we can implement this. So here is our final Sudoku solver which we're going to define today. And what we're going to do is we're going to do the same as before. We're going to filter out the valid grids after collapsing, after fix of prune. So fix is a new function that we haven't defined yet. And then we're going to apply choices. So the only change this time is that we're now, rather than applying the pruning function once, we're going to keep iterating it until the choice matrix doesn't change. And this means finding a fixed point of a function. A fixed point of a function is a value that when you apply the function to it, you get the same thing back again. So what fix is going to do is keep iterating the pruning function until it doesn't have any effect anymore, until when you give it a choice matrix, you get exactly the same choice matrix back again. So let me define the fixed point function. So fix is going to take something which supports equality, because we need to check if two things are equal. We need to check if the output, once we apply pruning, is the same as the input. So we need an equality constraint on here. Then we're going to take the function we're going to take the fixed point of. So that's the thing we want to iterate until we don't get a change. Then we take an input and it's going to give us an output. Okay, so the type's a bit weird, but the basic idea is very simple. We're going to take a function as an input here, and we're going to take an input to the function, and we're going to iterate the function as many times as possible until the output is the same as the input, and then we'll give back the result. Okay, so how does this work in practice? Well, what fix is going to do is you give it a function like prune, you give it an argument, and that will be, in our case, a choice matrix. And what it's going to do is, we're going to do a little equality test here. So let me just write down the definition, and then I'll explain, how it works. So the definition is very simple. We're taking a function f that we want to iterate until it doesn't change. We're taking an input to that function, And then what we're going to do is apply the function once, first of all. So we apply the function f, and we get a new output x prime. If the output and the input are the same, that means we have found the fixed point of the function. It doesn't change anymore, and we simply give back the result. Otherwise, we're going to call ourselves with the new output and keep iterating. So what this is going to do is keep iterating, in our case, the pruning function, until it just doesn't change the choice matrix. And you can try this one out on GHCI. If you start up GHCI and you say solve 3, the easy grid, it will give you a solution instantly. So it'll give you an instant solution, which is very satisfying. And in fact, it will solve any easy grid, not just the particular one which I've given you. It will solve any easy puzzle from the newspapers instantly. But there's a problem. Not every Sudoku puzzle is an easy one according to the rankings. There's other levels of rankings as gentle and difficult and diabolical and impossible and so on. And if you look in the source code, I've given you some other example Sudoku grids, and I've given you, for example, a gentle grid, which is a little bit harder to solve. And if you try solving with the third Sudoku solver, the gentle grid, it won't terminate anymore. And in fact, for the gentle grid, it'll end up exploring about 10 to the 29 grids again. And in fact, that's what you'll have coming out of here. For the gentle grid, you'll have about 10 to the 29 grids coming out. So it doesn't actually work in this case. So here are our basic declarations, because as usual, we're going to be using these quite a lot today. So just a quick refresher that a Sudoku grid is a matrix of values, a matrix of things is a list of rows of things, a row is simply a list, a value is a character, and choices is simply a list of values. So make sure you're all familiar with these basic data type declarations. So what we did last couple of times is we defined a few Sudoku solvers. So I'm going to quickly review these and also kind of talk through the problems with these, and that will lead us into kind of having a very efficient Sudoku solver, which we're going to end up writing today. So the first solver we wrote was a very basic one, and it was called solve, and it took a Sudoku grid as an input, and it gave a list of all possible Sudoku grids which solve that puzzle as an output. And again, if you want to just have one Sudoku grid, then you just simply take the head of that list, and under lazy evaluation that will just compute that and nothing else. So the way this actually worked is it was defined as a simple composition of 3 functions. It was a nice one-line program, and what we did is we filtered the valid grids after collapsing after making choices. So let's talk briefly through what each of these 3 functions actually did. So what choices does is it takes your initial Sudoku grid, which are given, for example, the easy grid, which we had, and it replaces each blank cell by all possible choices that we could have for that cell, 1 to 9. And it doesn't try and do anything clever, it simply replaces each blank cell by all possible choices 1 to 9. Then what the collapse function does is it considers each of the cells, and it considers all possible combinations of all possible values in each cell. And again, I mentioned maybe this should really be called something like explode, because this actually really explodes the search space. And then finally what we did in the end is we filter out the valid grids, and valid simply means that there's no duplicates in any row, any column, or any box. So in principle, this Sudoku solver actually works, but in practice we found that it didn't, because, for example, for the easy grid, at this point, coming out of the collapse function, there were 9 to the power 51 possible grids coming out at this point. And that's because in the easy grid, there's 51 blank cells. So when we consider all possible combinations using the collapse function, we get 9 to the power 51 possible grids coming out. So this Sudoku solver in principle works, but in practice, it will never terminate in anybody's lifetime. So we need to think a bit more. So what we did then is we thought about the idea of pruning out invalid choices. So this led us to our second Sudoku solver. So we had a Sudoku solver called solve2, and it had the same type as before. And it's defined in much the same way. So we filter the valid grids after collapsing, after pruning, and this is the new part, after applying the choices function. So this is basically the same as the first solver, except we've added one new function here in the composition. We've added the prune function. And what prune does is it removes any choices which occur as single entries in a particular row, column, or box. So for example, if you had a 1 in the top left-hand corner of your Sudoku grid, then there's no point in having a 1 anywhere else in that row or that column or that box, because you've already got a 1 in the top left-hand column. So that's what the pruning function is doing. And then what we found is that when you try that out with the easy grid, it does reduce the number of possibilities. So you get down to about 10 to the power 24 possibilities in here. Possibilities. But that's still an enormous number, so it's not actually tractable to solve Sudoku puzzles using this function. So then what we did is we introduced the idea of actually just iterating the pruning function, and this led us to our third Sudoku solver, which is the final one which we did last day. And what we did here is we iterated the pruning function after applying the choices function. So the only change here is we're now computing a fixed point of the pruning function. And a fixed point of a function is an input that when you apply the function to it, you get the same result back as you were given. Okay, so with the idea of computing a fixed point of the pruning function is we're going to keep on pruning out single choices from any row, column, or box until that isn't possible anymore. And then we'll call collapse, and then we'll call filter valid. And what we found last day is that this simple solve3 function can solve easy grids immediately. In fact, you could actually characterize easy grids as ones that can be solved using this particular function. But unfortunately, not every Sudoku grid, which you find in the newspapers, is easy. There's a whole hierarchy of difficulties. You have gentle grids, you have difficult grids, diabolical, all sorts of other ones as well. And in fact, when you try it with the gentle grid, out of the collapse function now comes about 10 to the power 29 possibilities that you need to consider. So this function will work fine for solving easy Sudoku grids, but unfortunately it's not sufficient to solve anything more complicated. So we need to think a bit more deeply. So the question now is, how can we solve any Sudoku puzzle that we can find in the newspaper, or in fact any Sudoku puzzle? And what we're going to see today is that the key is something called blocked matrices. So that's what we're going to be looking at now. It's the idea of a blocked matrix of choices. And we're going to come at this by introducing two simple concepts first. The idea of a choice matrix being void, and then the idea of a choice matrix being safe. And these are very simple concepts. So the first concept I want to introduce is that a matrix of choices is going to be called void if at least one cell has no choices. So an example of this would be if we had the top left-hand corner of our choice matrix, maybe we had a 1 here, no choices in the second square, and then a 2 and a 3 as the choice here. This would be void because there is no choice left in this square. Okay, and of course, if you ever ended up with a void choice matrix where you have at least one cell which has no choices left, that's never going to have a chance to lead to a solution, and that will be important to us in a bit. So that's the idea of what a void choice matrix is. How can we actually define what this means? Well, this is very simple. we can take a matrix of choices and we can return true or false depending on whether any of the cells in the grid are empty, so there's no choices left. This is a very easy function to define. We take our choice matrix M and we use the any predicate, or the any higher order function rather. And what any does is you give it a property like being an empty list, which is null in Haskell. Null decides if a list is empty, and any will take a predicate or a property and it will decide, does any element of a list have that property? So we're using any twice here, and what we're really saying, is it the case that any row has any empty cell? So this will return true if it finds any empty cell of choices in a matrix of choices. So that's the idea of a void matrix. The next thing I want to introduce towards defining what a blocked matrix is the idea of a matrix being safe. And we're going to call a matrix safe if all the rows, all the columns, and all the boxes are what's called consistent. And consistent is going to mean that they don't contain any duplicated single choices. So for example, if I had a top left-hand corner like this, and I had a 1 here, and a 2 and a 3 here, and a 1 here, and a 4 here, this would be an inconsistent matrix because I have a 1 here, and I have a 1 here as well. And if I ended up with 2 1s in the first row, that's never going to lead to a solution, because one of the basic rules of the game, or the basic rule of the game, is you have to have each of the numbers 1 to 9 in each row, column, and box exactly once. Okay, so this is the idea of safety. A matrix is going to be called safe if every row, column, and box is consistent in the sense that it doesn't have duplicate single entries. So let's define what it means for a matrix to be safe. So a matrix of choices is going to be safe. So that's going to return true or false. And this is a very easy function to define because I'm going to use a helper function. I'm just going to say if all the rows are consistent, so no duplicate single entries, and all of the columns are consistent, so all of the columns are consistent, and finally all of the boxes are consistent. So I'm just using my helper functions, rows, columns, and boxes. And of course, I haven't yet defined what it means to be consistent. So how does consistent work? Well, consistent just takes a row of choices. It's going to take a row of choices, and it's going to give back true or false. And all it's going to do is check, is there a duplicate single entry in any of these choices? So I can give you a little concrete example. So if I say consistent startup GHC and say, suppose we've got 1, 2, 3, 4 in the first box, and then we've got a 1, that's a single entry, and then we've got a 3 and a 4, and then we've got a 3. So that would be consistent because there's no duplicate single entries. So we do have 2 single entries here. We have a 1 and a 3, but these are different. So this is consistent. An example of something which is not consistent is if I take the same example and I just modify it a little bit. 2, 3, 4. So I have the 1 and I have the 3 and the 4. And suppose I had a 1 here. So now we have a duplicated entry. We have a duplicate single entry. This choices would never lead to a possible solution because we have 2 1s in the first row. So that's never going to give a solution because it violates the basic rule of the game. So we'll say that's not consistent. Oops. We'll say that's not consistent, and we get back the value false. Okay, so I'll leave it as an exercise for you to define this function. As I mentioned at the start of the course, I'm going to define lots of the functions that we use in the course, but from time to time I'll set little exercise to you, and if you want to do particularly well on the course, try and do these little exercises for yourself. So we've now got all the components that we need to define what it means for a matrix of choices to be blocked. So we take a matrix of choices and we give back true or false. And the idea is very simple. We combine the use of the void function and the safe function. So a matrix of choices is going to be blocked if either it's void or, so the double bar here is the Haskell or operator, or it's not safe. Okay, so what does this actually mean? So this part here means there are empty cells. So there's choices where there's actually no choices left. And what this part here means is there could be, or there are, duplicated single cells. Okay, so this is what it means for a choice matrix to be blocked. Either there's some cells which are empty, or there's some cells where you have a duplicated single choice in a row, column, or a box. And the key idea is that blocked matrices can never give you a solution. Because if you've got an empty choice, then you can never get a solution. If you've got a duplicate, say you've got a 1, 2 places in the first row, you can never get a solution from that point onwards. And you can ask yourself, why are blocked matrices really bad for our current Sudoku solver? That's solve 3, which we talked about a minute ago. And the problem is that a choice that leads to a blocked matrix will be duplicated many times by collapse because it considers all possible combinations. So if we go back to our final solver here, when we apply the collapse function, if we have reached the point where we have a blocked matrix, then in the collapse function, that's going to be duplicated many, many times because the collapse function will consider all possible combinations of choices. So thinking about these blocked matrices is actually going to be the key to coming up with a very efficient Sudoku solver. So the idea here is we're going to actually expand choices out one cell at a time. And what we're going to do is filter out resulting matrices that are blocked before expanding further cells. And that means if we find the choice matrix which is blocked, we just abandon it completely rather than passing it into a collapse function or the collapse function, which is then going to expand that and consider zillions of possibilities which never have the possibility to succeed. So here is our final Sudoku solver. I'm going to call it solve 4. And it's going to be defined as a function composition. So what we're going to do is we're going to call a function called search after a function called prune after applying choices. Okay, so let's understand what's going on here. So the first part here, prune after choices, is pretty much the same as what we had before. Choices simply takes the initial Sudoku grid and replaces each blank square by all possible choices between 1 and 9. Then we apply the pruning function once, and then we're going to pass the result of that into a function called search, which is now what we're going to write. And you might be thinking, well, why didn't I write fixed prune here? But actually, we don't need to do that. It actually turns out to be more efficient if we don't iterate the pruning function. And I'll come back to that point in a bit. Okay, so let me write then the search function, which is going to do all the work for us. So what search is going to do is it's going to take a matrix of choices and it's going to give me back all possible Sudoku grids which solve that puzzle from that point. Okay, and again, if you just want one, you simply take the head of that list. So we're going to define it by case analysis. So we pass in a choice matrix M, and then we're going to have 3 possibilities. So I'll use a simple guard here. The first one is if the choice matrix is blocked, that means it's never going to lead to a solution. So we may as well just stop at that point. Okay, and this is the problem, or one of the key problems with our previous Sudoku solvers. They didn't do anything in particular about blocked choice matrices, and if one of those hits the collapse function, it will consider all possible combinations of a choice matrix, which is never going to succeed. So what we're doing here is we're chopping off matrices which never have a chance to succeed by checking, are they blocked? And if so, we're simply going to return the empty list because there's no possibilities for a solution. Maybe we've also reached the point or we have reached the point where we have a solution. So if every cell only has a single choice left, and I can define single down here, what single does is it takes a list of things and it gives you back true if there's only one thing in the list. So I could say if you have a list with one thing, and I'm here using the Haskell wildcard pattern down here, which is the underscore. If you have a list with one thing, I could return true. And if I have any other list, I return false. Okay, so this is the simple single property. Okay, so let me get rid of that. So what this is going to do is, if we've reached the point where every entry in the grid only has a single choice, it turns out we will have actually solved the puzzle at that point, and all we'll simply do is we will call collapse. Okay, so if there's only one choice for each cell, the puzzle is done, and we just call collapse, and that will simplify it for us, and we're done. Otherwise, we need to do a bit of work. So what we're going to do is we're going to use a little list comprehension here, and let me write it down, and then I'll explain what's going on. So we're going to expand, and then we're going to have another generator here. So here's the code for the other case. So what's actually happening here? Well, first of all, what we're going to do is we're going to expand our choice matrix. And expand is a function which is going to behave in a similar way to collapse, except it's only going to expand the first cell which has more than one choice. So collapse considers all possible choices for every single cell in the grid, and that leads to a kind of combinatorial explosion for many non-trivial examples. What expand does is it only expands the first cell which has more than one choice. And again, you could look at the definition for this in the notes, which are freely available on the web page. But actually, I think it's a very nice exercise again. Try and define the expand function. So what we're doing then is we're expanding, and that will give us a bunch of matrices, potentially up to 9, if there's 9 possibilities left for the first square, which doesn't have a single choice. Then what we're going to do is for each of those matrices, we're going to prune it to eliminate any silly choices which were still left, and then we're going to pass that back into the search function again. And then what we're going to do is collect all those grids. Okay, so this is a nice kind of 3-line function definition which implements the idea of searching. And this is basically our final Sudoku solver now. This one here is a 1-line program. Well, actually not really a 1-line program because we've defined 3 other functions, search, prune, and choices. And this can actually solve any newspaper puzzle in an instant. A couple of points to note here. We don't any longer need to check for valid grids. You notice there's no filtering valid at the end here, and that's because of the way the grids are actually constructed. If you think about it and you kind of work through an example, maybe a small example, you'll find the grids which come out of this searching process are always guaranteed to be valid because of the way they're constructed. The second point I'd make is, again, I mentioned about pruning. We don't actually need to fix prune here or down here. If you fix prune here in both of these points, it's a completely valid thing to do, but it actually turns out to make the program a little bit slower, at least last time I checked. But that's the kind of thing you might want to run some experiments with. If you iterate the pruning process, I think it makes it slower, but you can try that for yourselves as well. So what we're going to do now is I'm going to move to using GHC and give you a little bit of a demo of how this solver actually works in practice. Okay, so I have a terminal window here now, and what I can do is start up the interactive version of the Glasgow Haskell compiler, GHCI, and I can input my Sudoku solver to it, and that all loads up fine, which is great. And we can have a look at the code, and you can see all the familiar stuff which we've been working with in here. Here are the basic data types. If we scroll down a bit, you'll find a number of example grids. So here is the easy grid, for example. If we scroll down a bit more, here is a gentle grid, which is a bit harder to solve. Here's a diabolical grid, which is harder still. This is an interesting one here. This is one which potentially requires backtracking to solve. So you may need to revisit your steps rather than just applying the basic rules of the game. And we'll see if our Sudoku solver can work with this one. The final two ones up here are particularly interesting. Here is a minimal sized grid. So this grid is mostly blanks. It's only got 17 values filled in, but it still does have a unique solution. And at the time when I was doing this, this size of grid, 17 values, was the smallest grid which was known to have a unique solution. So this is a particularly challenging problem for a Sudoku solver. And we can also, for fun, just try running a blank grid as our solver and see how it works out. So let's try some examples. So we could try the easy grid, that's no problem. We could try the gentle grid, no problem as well. Let's try the diabolical one. Yep, works fine. Let's try the unsolvable one. Unsolvable. That one works fine, that's instant as well. It's no problem for our solver. Let's try the minimal one. Oh, it doesn't terminate quite as fast, but if we wait about 5-6 seconds, then it will give us our solution. We'll come back in a minute to see how we can make this actually even faster. And for fun, let's try the blank grid as well. And of course, this is just going to spew stuff up the screen because the blank grid's got no constraints on it at all. So you can fill in numbers all over the place and get a very, very large number of solutions. But if we just wanted the first one, we can say head of solve for of blank, and we get the first one. And if we wanted 10 solutions, we could exploit lazy evaluation and just say we want take 10 of solve for blank, and we get the first 10 solutions, which is nice. So now let's return to the fact that when we did solve for of minimal, it didn't terminate as fast as the other ones. It took about 5 or 6 seconds, even on quite a fast machine here. So let's think about how we could make this even faster. And actually, we can make it faster just by using the Haskell compiler rather than the Haskell interpreter. So what I've done at the end here is I've included a simple main, just like you have in most programming languages, and it's a purely interactive program. And what it's going to do is first call the solver with the minimal grid, and then there's only one solution, so we'll take the head of the resulting list, we'll convert that into a string, and then we'll print that string on the screen. So now we can think about compiling this. So I'll leave GHCI. And now I will type GHC, which is the compiler. I will type -02, which turns the optimizer on full. And I will type sudoku.lhs, and that will compile it for me. And now I have an executable file. And if I run that, so /sudoku, then it will terminate much more quickly now. So this is now terminating in about half a second rather than 5 or 6 seconds. So it's about kind of 10 times faster. So what we've got here in the end is a highly efficient Sudoku solver which can solve essentially any Sudoku puzzle in more or less an instant.